All right, back for part 3 of chapter 9. Now, in this part, we're going to take a little scenic route around some of the discoveries that were also made. So, some related things dealing with light, and then what's happening with these little electrons. So, let's see what we can find. Here we can see some really cool effects that are going to deal with energy transitions as electrons go from one level to another. So we're going to look at fluorescence and phosphorescence and see what the slight difference between these are. So fluorescence is like your neon clothes. Or if you happen to be in a place that has black lights, your clothes are going to appear like they glow, like your teeth are going to glow also. What fluorescence does is it absorbs light in the UV region. So if you remember, the UV is just outside the violet region, so it has a shorter wavelength and a higher energy associated with it. So it absorbs this UV light and then it re-emits it in the visible range. So it's like more light is there than what we see. So remember, we can only actually detect visible light with our own eyes. We're being bombarded with all the other wavelengths also, but that's all our eyes can see. So what something that's fluorescent will do is it absorbs that UV and then it re-emits it in a light range that we can see. Now, phosphorescence is slightly different. What it does is it absorbs that light, but then the electrons take a long time for it to finally drop. And so this is going to be something that appears to be a glow in the dark. So if you've ever had the stars up on your bedroom, it's okay, you can admit it, that glow in the dark, those are phosphorescent. So fluorescence and phosphorescence. All right, so a few more discoveries. The first thing is the element helium. So helium is a noble gas. It actually took a long time for it to be discovered. It wasn't discovered until 1863. Now, how it was discovered is scientists were taking spectra of light sources. So remember, we saw that with hydrogen, you get a certain spectra. Well, if you take a spectra of a certain light source, you can actually figure out what elements are involved. So they would do that with, in this case, they were using light from the sun. And so they took light from the sun and they're trying to figure out what elements it has. Definitely has hydrogen, but then there were some other lines. And so they figured out it was another element called helium. Now, it took them 27 years to actually find it here on Earth. It was trapped in a uranium mineral, but it's here also. So that was helium. Now, another thing that kind of deals with this whole idea of spectroscopy is a microwave oven. You're like, wait a second, that's what I use to cook my popcorn with. Yes, it is. But this can be based somewhat on molecular spectroscopy. And this is going to deal with spectra and energy levels of molecules instead of specifically elements. So it turns out molecules also have quantized energy levels. Now, how a microwave oven works is that microwaves, and remember that's a type of EM radiation that is longer than visible light and infrared light, but it's a little bit shorter than radio waves. Now, usually microwaves are on the length of a couple centimeters is pretty common, and it turns out that they're just the right length that they like to excite water molecules. So the water molecules, in their excited form, move around more. And if they're moving around more, they have more kinetic energy. And if they have more kinetic energy, that means their temperature has been raised. So how microwaves work is they send out these little microwaves inside that microwave oven. The water molecules absorb that energy, and it's just the right conditions where the water molecules get excited and it heats up your food. Now, a couple of tricks for you. Um, you have to have water in your food to be able to heat it up really well. If you have food that's really, really dry, it's not going to heat up as evenly or as well. So you might need to add just a little bit of water to it. I'll have to do that sometimes with rice. It'll dry out just a little bit. Add some water to it. It'll heat up so much better. The other thing is sometimes you'll notice you'll get hot and cold areas in the food. Well, that's because those microwaves, they don't travel. They can't penetrate very well. So you need to stir your food or have a thin layer of it. Stirring is a really good idea. Or let it set once it gets out of the microwave a few minutes to help allow it time to reach a thermal equilibrium. So, yeah, microwaves. Who knew? All right, a couple more discoveries because, we're on a roll here. Let's talk about X-rays. Oh, that's another type of EM radiation. Little bit shorter wavelengths than our UV. So we had visible and then shorter as UV. And then even shorter than that, we have X-rays. And then later we have gamma rays. So X-rays were first discovered in 1895. Yes, they were there beforehand. We just learned about them in 1895 by a gentleman by the name of William Röntgen. Now, originally they were called X radiation, X for unknown. They didn't really know what they were. They noticed a fluorescent paper near a gas discharge tube started to glow. Now, of course, we use X-rays today to look at bones and see if you broke a bone or if you have a cavity in your tooth or something like that. The picture on the top actually shows a hand in it. There was a little bit of a hunting accident, and it has buckshot, so all those little pellets in there. They're trying to see where they're at and everything. Another discovery that's related is going to be a laser. A laser stands for light amplified by stimulated emission of radiation. So it turns out some substances like ruby crystals and carbon dioxide have what's called a metastable excited state. So the electrons are at the super excited state. So what we can do is we can shoot it with a photon of same energy, and instead of having like one in, one out, we send one in and two photons pop out. They spread very, very little when they travel. So then we can actually get like a laser beam. Scientists have reflected a laser beam from Earth off of a mirror on the moon from astronauts to accurately measure the distance from Earth to the moon. We also use lasers for optical fibers for communications, diagnostics, and surgical tools. If you know somebody that's had laser eye surgery, I have had that. Oh my gosh, it is life changing. You will still need reading glasses after you get to the age of about 40 if you ever do decide to do this. But it, yeah, man, I had really bad astigmatism and I was very nearsighted. Anything past about my arm length, it was blurry, and it's just amazing how much better I see now. Another one, optical scanners for barcodes are also going to use those lasers as a light source. All right, so we need to start bringing this back to the electrons and the atoms and how the idea of the atom developed over the years. So we need to talk about something called the Heisenberg uncertainty. Heisenberg was a German scientist. His mentor was actually Bohr. Do you remember Bohr from a couple of slides ago that had the planetary model? Of course, once World War II came about, that relationship became very strained. Now, one of the things that Heisenberg was looking at is trying to figure out the location and the velocity of an electron, and it turns out it's impossible to know a particle's exact position and velocity simultaneously because they're so small. Whenever you take a reading of one of it, it affects the other. Now, okay, so that didn't make a whole lot of sense to me back in the day. But here's my explanation or my comparison. So hopefully this will help out just a little bit. Let's say you're driving down the road and maybe you're exceeding the speed limit just a little bit. Or maybe you're not. Maybe you're driving very, very safely and cautiously. It's great. But off to the side, there's a police officer and they get out their radar gun and they want to see how fast you're going. Now, with that radar gun, they send out a radio wave or a microwave, depending on what type they have. That wave does not affect your car in any way, unless you happen to see the cop and you slam on your brakes. But that wave isn't going to like knock the car off of its path, or it's not going to cause it to slow down or speed up by itself. Um, but that's because a car is really, really big. But let's imagine we try to do that same type of experiment, but instead of a car, we have an electron, and the electrons are so very tiny that if we send some sort of a ray or something in to be able to figure out the speed, it's going to knock it out of its location. Or if we have something that looks at the location, it's actually going to change the speed. So it turns out there's a lot we really just don't know, and that's what Heisenberg uncertainty is going to really emphasize. We cannot figure out, it's impossible to know the exact position and velocity of an electron at the same time. So what we're going to deal with is probabilities. It's likely that the electrons are going to be in these areas versus these areas. So now we need to talk about that not only light has both wave and particle characteristics, that electrons do also. So that we have this dual nature of light and dual nature of electrons. Now, de Broglie waves are going to start talking about what happens to those electrons. So these are called waves or waveforms that are associated with moving particles. So moving particles have wave characteristics and particle characteristics. The de Broglie equation down at the bottom is going to look at that. Don't worry, we're not going to do a whole bunch of math problems here. We start off with lambda, that's going to be our wavelength, is equal to h. Now, h is Planck's constant. Remember Max Planck from before. It's just a constant. It's a set number. We divide that by m. Oh, now here's what's important. We had our lambda, which is a wave characteristics. Now that m, that's mass. That's a particle characteristic. So waves and particles, and we have some sort of a connection between them now. And then v in this case is going to stand for velocity. So what this says is that every particle has a wave characteristic and every wave has a particle characteristic for our light and for our electrons, but we don't necessarily see that wave-like functionality. So if I was to take a baseball and throw it, you're not going to see it move in a wave-like fashion, even though this is saying there's a wave-like fashion to it. Well, let's look at this equation again. So we have our wavelength. Now, the bigger the wavelength, the more we're going to be able to observe it. If the wavelength is really small, it's going to be too small for us to observe. And then the other thing we want to look at is that m, that velocity. The bigger that velocity, not the velocity, we're going to look at the mass. Oh my goodness, I'm getting my words all mixed up. We're going to look at the m, the mass. The bigger the mass is, the smaller the wavelength, because we're dividing by that number. And the smaller the mass, the bigger the wavelength. So back to my baseball example, if I compare a baseball to an electron, the baseball is huge. So the mass is going to be much larger for a baseball compared to an electron. So the wave-like fashion, the wavelength, for a baseball is going to be really small because we're dividing by that larger mass. But for an electron, which is really tiny, that's where that wavelength is going to become significant enough that we can start doing some stuff with that. Now, if we take that dual nature and we take the planetary model and we kind of combine a lot of this stuff together, we end up with the electron cloud or the quantum mechanical model. This is by a guy named Erwin Schrödinger. Oh man, fascinating person here. So here we're getting into the idea that we have the nucleus, the electrons are around it, But instead of the electrons moving in a circular path, they actually move in a wave-like fashion. But it gets a little bit more complicated than that, because with Heisenberg, we learned that there's places that the electrons like to be and don't like to be. And so this is going to start combining it all together. Now, yes, there are future models after, or there are significant models after this, but this is the one where we usually stop kind of talking about the history of the atom at this point. Yes, we could get into the quarks and the strings and everything else, but let's stick with this electron cloud or quantum mechanical atom, where the electrons move not only in um, shells, but they move in a wave-like pattern. Now, this was able to explain multi-electron atoms. So anything with more than one electron, anything on the periodic table past hydrogen, we now have some sort of an explanation for this. So that's awesome. But I tell you what, since we're on this slide, let's talk a little bit about Schrodinger, just a little bit. Have you heard about Schrodinger's cat? Oh my goodness. So Schrodinger's cat was used to illustrate the absurdity of the existing views of quantum mechanics. The idea is you have a cat inside of a small box with a small amount of a radioactive substance that once it decays, it releases hydrogen cyanic acid, which will kill the cat. But we don't know if it's happened or not. So if we don't know if the cat is alive or dead, and so we have just this who really knows what's going on at this particular moment in time type thing. That's Schrodinger's cat. So a little bit about Schrödinger. He is Austrian. He left Germany in 1933 due to a dislike of the Nazis, and he wrote a letter saying he didn't like the Nazis, so he had to move around a lot. He ends up in Ireland. Now the story goes that he is a bit of a womanizer. He's got a wife, mistresses. He actually has an open relationship with his lab assistant's wife, and they end up having a kid together. Um, Scandalous involvements with students and all sorts of things. But one of the things that I think is really interesting in science and in chemistry, of course, my favorite part, chemistry, is that a lot of times we try to kind of pigeonhole it. So if you were here on main campus, my chemistry class is in this part of the building. And if you go across the hall, you can talk about microbiology. And if you go down here, you've got biology. And this lab is for physics. And a lot of times we try to separate out the different sciences. And if you wanted to talk social sciences, you got to go to the other building for that one. But in real life, everything's kind of interconnected. So what Schrodinger does back in, let's make sure I get the right years in here. In 1944, he writes a book called What is Life? Now, this book inspired others to research genes, and it led a guy named James Watson to actually start studying that also, and that led to a discovery of DNA. So I know a lot of times we like to say we're in one small area, but it's amazing how all the sciences are intertwined together. Now, I hope that you get a feeling for that, at least for the physical science portion in this class. They're all kind of intertwined together. Dalton, remember that was the billiard ball model? One of the reasons he started studying atoms was he had an interest in meteorology, about the weather and hot air ballooning. And so then he was interested in the gases because our atmosphere is made of gases. And then that led to an interest in chemistry. So just recognize the fact that a lot of interest can overlap, and we get to use all of those special interest to be able to learn more about the universe. So that is it for chapter 9. Yay! Now, like I promised, okay, there was an equation in here I showed you, but there really wasn't any big math at all to worry about. So that's atomic physics. The next chapter we'll deal with, we're going to look a little bit at nuclear physics and see the start of chemistry.